Hello. In this lecture, we will discuss 0-1 knapsack problem. As you know, the 0-1 knapsack problem means given the set of weights and associated values and a knapsack capacity, we want to pick up those weights such that the value of all the items in the knapsack is maximum. Previous lectures we discussed job assignment problem, traveling salesman problem using branch and bound, and we look at how do we apply this branch and bound problem, use branch and bound technique to 0-1 knapsack problem. Again, the examples and material is from the Horowitz textbook, which is this, and the resources. There is another lecture on YouTube you can look at, which also explains some way the 0-1 knapsack problem, what we cover in this lecture today. So what we are trying to do, if we looked at in the previous cases when we looked at branch and bound for the traveling salesman problem or the job assignment problem, we are basically trying to build a state space tree, and we are searching the tree one node at a time, choosing a node carefully to see how to explore the next node. And the efficiency of the branch and bound depends upon how do we explore. So general algorithm to search or explore the state space tree is the following. So essentially look at if tree is when you're searching for it, when we reach a node which is answer node, that is when we reach the optimal solution. When we reach an optimal solution, we are done and we can return. If not, then we need to explore that node. And how do you explore? Initialize list of live nodes to empty, and then look at all possible children for this. For each child of it, look at if it's answer node, output the path from X to the child node to the node explore and return. If it's not a child node, then add this child node to the list of live nodes as long as it's live node, and define the parent so that you can trace the path back, and we stop when L becomes empty. Otherwise, you take the next node and continue. So this is a generic algorithm for searching the state space tree that we build, and keep doing it till essentially the list becomes empty. This one becomes empty, we come out and say no answer node, or some point in time we'll get an answer node, output the path. Now whole complexity or the efficiency of the algorithm depends upon what kind of list we are maintaining here. So primarily the list that we maintain, L, is it a queue, is it a stack, is it a heap, is it some data structure, and how do we add the elements, and how do we take out the next element. The efficiency of the algorithms depend upon that. So let's look at what could be possibilities. We'll consider three possibilities. One is we implement the list as a FIFO, as a queue, that is first in, first out. So that means when we add element to the list, they are added at the end of the list and they are removed from the beginning of the list. So that is next cell is taken as first element out, and when elements are added at the end, so whichever element goes first, they maintain a queue, and this is how the other choice is we implement as a stack, and stack is called LIFO, last in first out. It's more like a stack. That means the last element that goes in, there's the first element that comes out. And if we look at LIFO, is kind of indicates depth first search, and that's why it's also called D search or depth first search. In contrast, when we put in a queue, it basically becomes breadth first search. And the other choice is we implement L as a heap, and we maintain a min heap. That means children of a node are always greater than the key value of the parent. And so we always take the element out. The next element will always take as the smallest element and proceed. And that basically what is called is least cost search. And in this lecture today, we'll look at how do we use this least cost, how do we use this least cost mechanism to explore the state space tree and find out the max value in a knapsack case. So what is the knapsack problem? Just to recall, as you probably see, knapsack problem is given n weights at W1, W2 to Wn with their respective values given as V1 to Vn. In the book, this is given as profit, P1 to Pn, so both are same, doesn't really matter. And a knapsack capacity of M. And it's obvious that if I sum all the weights W1 to Wn, sum of all weights would be greater than M, because if it is less than M, it becomes a trivial problem and all weights can be chosen. So goal is to find a subset of items from W1 to Wn such that the value of the items in the knapsack is the maximum. So essentially what we're saying is take the value of the items and with the constraint that item has to be taken in full. We can't take it partially. So it's not a partial knapsack, it is a full knapsack. So either you take element in full or don't take it at all, and hence it is called 0-1 knapsack. Note that both values, the W's, the weights, and the capacity among integers, whereas values can be non-integer, could be real number, anything of that kind. Now you understand we are trying to maximize the value of the knapsack, and therefore this 0 knapsack is also called maximization problem. Previous lectures we used branch and bound for job assignment and traveling salesperson problem, and there we're trying to find minimum cost tour for TSP or min cost job assignment. So branch and bound is basically used for minimization problem, and we need to see how do we apply this branch and bound, which is a minimization problem, to solve 0-1 knapsack problem, which is a maximization problem. So that means we need to somehow convert the knapsack problem, which is a maximization problem, to a minimization problem. So if we look at mathematically, the knapsack problem is defined as maximize the values vi xi, where xi could be 0 or 1. Look at all the elements. So if an element is taken, xi would be 0. If ith element is not taken, if element xi is taken, value of xi would be 1. If xi is not taken, value of xi would be 0. Sum total of all weights should be less than equal to the capacity, and what we want to do is maximize some of those elements which have been chosen. And as given, x can be either 0 or 1, and we need to look at all the elements. This essentially is the maximization problem. So how do we convert maximization to, look, any number, if it is larger, if we look at two numbers, we know that if A is greater than B, then minus A is less than minus B. So if A is greater than B, the max of A and B is A, then minus A would be min of A and B. So if we convert these, maximization value, you convert the values to negative, it basically becomes a minimization problem. And since we are looking in terms of cost, we will, rather than values, we call it a cost. So if we take the V's as negative value, we convert the 0-1 knapsack problem to cost minimization problem, and effectively if you can find the minimized cost, corresponding value Vi would basically give us maximum knapsack value. Other constants remain the same, that sum of all the weights should be less than the knapsack capacity, and this we need to look at. And how does our state space tree works? If you look at state space tree, we basically can implement two ways, like what we have seen in some of subset problem. Either we can take fixed tuple value, that means for each element we choose xi 0 or 1, or we keep as an index, and in this case we'll basically look at fixed tuple size, that one variable xi for each weight, and we will not look at index of the weight. So How do we form the tree, state space tree, and how do we explore it? So we'll say fixed tuple size. That means for each element, we'll have a tuple variable. So for ith weight, we'll have a variable xi whose value can be either 0 or 1. Now, when you start a node from going from one state, from swinging one variable to next one, we'll take the next weight. It can have only two values. That means in my state space tree, my each node can have only two children. First children would be xi is equal to 1. So if I am node I look at node I plus 1, though either xi plus 1 is equal to 1, this is left child, or if I take xi plus 1 as 0, that becomes my right child. And this is what we'll basically do. And once you know the fixed tuple, then we can easily convert into index of the weight problem, the variable tuple size, essentially pick up those indexes for which value is 1 and take their respective tuple index. That gives me variable size problem. Now to implement this minimization problem, we'll define two terms. One is called cost and other is called upper bound, what we had done in the previous cases of TSP and job assignment. So we'll define cost per node and we define upper bound per node. Since we're looking at the cost, we're taking V as negative, so we define Cx as for each answer node. If answer node is x, from root till that point, nodes are considered, look at the values. So this value, sigma minus 1 to I, 1 to n, Vi xi, is that minimize this value, and this is the cost value. And if a leaf node is infeasible, we'll say value is infinity. If for any intermediate node, we'll define recursively as, because this intermediate node, we'll be exploring it till it goes to the leaf. So we'll define cost of any intermediate node would be minimum cost of its left child and right child at that value. And this is what we'll basically define. Now look, if I need to compute value of intermediate node recursively in terms of its left child and right child, it becomes computationally very expensive, practically exponential, and that means I cannot use the mechanism. So we need to find some other way of computing the cost. The way we'll define cost is we'll define C hat x, a heuristic value for x, Cx, and what we say is we'll keep computing the cost of the knapsack, the whole knapsack, till we encounter a weight whose cannot be included because including that weight exceeds the knapsack capacity. So looking at my theoretical cost, I'll even, for cost computation purposes, I'll basically take the last element which can't fit into the knapsack as a partial weight. So to computing cost, I look at only partial knapsack, but for my bound case, I will not use the partial case since ultimately I'm interested in 0-1 knapsack. So my computation depends upon upper bound, where we will not use the partial value, but for cost purposes to compare, we'll use the partial value. And then we'll see how these two will be using to build our state space tree, and then how do we explore it. So fundamentally, if you look at, ultimately we would like to have my heuristic value should be less than my upper bound because we're looking at minimization problem, and as and when if cost becomes more than the upper bound, we need to kill that node. So the moment the cost becomes upper bound, we kill that node, and that's why we can prune this search there. And this technique we'll use in our 0-1 knapsack implementation. So how is our 0-1 knapsack? Let's take an example to understand how it gets implemented. Let's consider a set of 4 items with the 4 weights W1, W2, W3, W4, and a knapsack capacity of 15, 4 elements, and the weights are given as W1 is equal to 2 units, W2 is 4 units, W3 is 6 units, and W4 is 9 units, and the respective values are 10 for weight 1, 10 for weight 2, 12 for weight 3, and 18 for weight 4. So using these values and using the weights and a knapsack capacity of 15, how do we do least cost, what we say least cost branch and bound, known as LCBB. So least cost branch and bound approach for our knapsack problem. As we said, we'll be using fixed tuple, and fixed tuple means since you have 4 elements, we're using 4 variables x1, x2, x3, and x4. Each of them can take value 0 or 1. And for each node, when we explore, starting from root till we go to the leaf, we will compute the value, heuristic value Cx, and we'll look at the value of bound, and the whole tree wise will maintain a variable called upper. This will be called as best solution so far. So our upper would be the best solution so far. Sorry, upper would indicate the best solution, and we, as long as, so upper would always be lowest of all the ux which we have computed so far, and the moment we find any c hat, the cost becomes more than the upper. That means we need to discard that node because that's our lowest bound, and cx means we are exceeding that cost we cannot achieve. So there's the more than the upper, which is not a minimization because value would be more than the best solution. So there is no point exploring. We stop right there. So as usual, we'll start at node 1, a start node, and then using least cost approach, that basically means we'll be using a heap and keep building a heap, and from the heap we always take the node which has the least cost value at any point in time and explore to build the tree further. So let's just start from the building our state space tree using LCBB approach, least cost branch and bound. On the right side you can see that this is our cost. So 4 elements, weights are 2, 4, 6 and 9. Their respective values are 10, 10, 12, 18, and knapsack capacity is 50. So we start with node 1, and how do we compute Cx? As we said, we need to look at those values, keep adding from beginning so that my capacity doesn't exceed. So first I take 10, sorry. So first node I weight 2, then I look at 6, 2 plus 4 becomes 6, still less than 15. Then I take 6, 2 plus 4 plus 6 is 12, still less than 15. That means these three weights contribute fully, but the moment I look at the weight 4, the total weight becomes 21, which exceeds. So for computing my cost, I'll need to use weight 4 partially, and I'll take only 3 units out of it. That basically means I take 15 minus some of these, which is 12, and then take respective value. So my computation would be for weight 1, 10, for weight 2, 10, for weight 3, 12, which is this, and for weight 4, since I have 3 capacity left, I'd say 15 minus 12, which is sum of the 2 plus 4 plus 6, 12, 15 minus 12 is what gives me. So if we look at this, gives you 10 plus 10 plus 12 is 32, and this gives you basically 6. Since we're looking at the cost, we're looking at the minus value. So my cost for root node is minus 38. But my upper bound, I will not take the partial W4. I'll take only W1, W2, and W3. So my upper bound for this node is 10 plus 10 plus 12, and we will not take this. And hence my upper bound is minus 32. This is what we get. Now this is the only node so far. We add this, and we know upper cost, since upper is initialization, we see upper value is minus 32. First time computing, we initialize that. Now we need to explore this. This is the only live node available right now. This is not a leaf node. So how do we start exploring? We'll take two values. Consider weight 1. So weight 1 either can be included or weight 1 doesn't have to be included. So if weight 1 doesn't get included, x1 becomes 0. If weight 1 gets included, x1 becomes 1. So explore these two children. X1 is equal to 1. That basically means we build it node. So this becomes node 2. And when x1 is equal to 0, this gives me node 3. And that means node 1 is taken out. Now my live nodes are 2 and 3. Now look at live node 2. Now when x1 is equal to 1, what is my cost value? See, if I keep including, remember, I'm excluding the path where this node is included, and hence whatever my cost was is not going to change. So if we look at when x1 is equal to 1, that means I need to include this weight is already included, and it will go 2 plus 4 plus 6, which makes it 12. And the moment I include 9, it becomes exceeding the natural capacity. So I do partially, and so computation wise, basically again, W1, W2, W3 contribute fully, and W4 contribute partially, and the cost will remain same as what the root node is, which is minus 38. And same is true for my upper bound, which because I'll include only these 3 nodes, will not include the 4th node. So my upper bound is minus 32, and this is what I assign the cost and 30. Now look, my previous upper bound was minus 32. My current upper bound is still minus 32, so there is no change. It remains the same. Let's explore with node 3. Now we look at node 3. That means x1 is 0. That means we are not including this item. So let's look at, that means we include 4 plus 6 becomes 10. And the moment we use 9, it becomes 19, exceeding natural capacity of 15. Since 4 plus x is 10, that means we can take only 5 units of the node 4 for my partial computation. So the cost becomes 10 for first node, 0. For second node, it is 10. I take 10. For third node, I take 12, which is 12. And fourth node, I'll take partial weightage, which is basically 5 by 9 into 18, which again gives me minus 32. But my cost this time would be, if you look at the cost, look at the upper bound, I'm not taking this because this is excluded, and this exceeds my capacity. So for my upper bound, I'll take only these two values, 10 and 12. So if you look at my upper bound for node 3 becomes minus 22. So put it together, my cost is minus 32, my upper bound is minus 22. Now this minus 22 is greater than minus 32, so my upper bound does not change. Now at this point in time, if you look at, my live nodes are 2 and 3, and this is how they have been added. So my live nodes are 2 and 3, and I'll explore with, because the FIFO implementation, it is the least cost implementation. If you look at the cost, in this case, node 2 has the cost minus 38, node 3 has the cost minus 32. The lower cost corresponds to node 2, so we'll explore node 2 and we keep 3 in the list of nodes. So now that means I look at next variable x2. X2 could be again 1 or 0. When I take x2 is equal to 1, I get node 4. X2 is equal to 0, I get node 5. And then I have to compute the values for node 4 and node 5. So look at node 4. Since I'm including the item, including the path, this cost is not going to change. It's again going to be, if you look at, weight is 2 plus 4 plus 6, and this 9 is taken partially. So my cost for node 4 would be minus 38, and my value for upper bound for node 4 is 10 plus 10 plus 12, which is minus 32. And if you look at my u is minus 32, my upper is also minus 32. So this value is no less than this, so my upper does not change. Now I explore, so assign these values. Now I explore node 5. Not node 5. I need to explore node 3 because in the FIFO, my list of elements are the 4. So I'm just computing and see, do I need to add or what I need to do? So let me compute 5. When I compute 5, I'm excluding this weight 4. When excluding this weight 4, I'm including 1. So I'm including this, I'm excluding this, then I'll include this, and then there come 2 plus 6, which is 8. And if I include this, it makes it 17, which exceeds the capacity. So compute cost, I'll take only partial amount, which meets this value of 15. So 2 plus 6 is 8. I need to add only 7 parts of it. So for cost computation, I'll take weight 7 to compute, and this cost becomes 10 for the x1, 0 for this case, 12 for third weight, and this is partial weight 7 for the fourth weight, and value becomes 36. What does my upper bound becomes? I'm taking this value, I'm not taking this, I'm taking this value, and since this has two partial, I'm not taking this value. So my upper bound becomes 10 plus 12, which is 22, and it's negative, it becomes minus 22. So my upper bound is minus 22. Now look at my upper corresponds 32, upper does not change, and we are fine. Upper remains same and doesn't change. So what do we do now? Live nodes are, now I have a 3, which is the previous case, 4 and 5. I need to explore lowest cost. Lowest cost happens to be node 4. So we'll basically explore the node 4 and continue. Let's look at the node 4. Now node 4, again, I look at the weight 3, either I can include it or exclude it. If I include it, that is x3 is equal to 1, I get node 6. And when node 6, the weight is, so here this is included, and I'm including this already becomes 8. So again, 2 plus 4 plus 6 equal to 12. I only take partial value of 3. And so if you look at my cost and my upper bound will not change for node 6. If you look at in this way, anytime I take x value is equal to 1, my cost and upper bound remains whatever my parent is, because I'm simply, that node would have been included, we are not changing. So value for this remains my 32. This is what we do. And since my upper bound is minus 32, which doesn't change, so we are fine. Now let's compute the value for 7. Now x3 is not included, so we are not including this weight. When you're not including this weight, that means cost will consist of 10 plus 10 plus this variable 9. So we look at the value 2 plus 4, 6, 6 plus 9, 15. It exactly matches 15. That means I can take W4 completely. So my cost becomes 10 plus 10 plus 18, and which is the case before. But my upper bound also becomes, if you look at my upper bound also becomes, because I'm not including the weight third, and so my upper bound becomes 10 plus 10 plus 18, which is minus 38. Now look, my upper bound has decreased. It was minus 32 before, and now it has become minus 38. So upper bound changes, and because upper bound changes, I need to update the best solution to 38, minus 38. Now look at what has happened. Now because my upper bound has changed, I should not consider any node whose cost happens to be more than minus 38. So if you look at the node 3, and node 3 cost is minus 32, which is greater than minus 38. Node 5 cost is minus 36, which is greater than minus 38, and that means there is no point considering this node 3 and 5, and thus we need to basically kill these two nodes. So the nodes left are 6 and 7. Those becomes my live node, and I take the least cost. Either I can take node 6 minus 38, or I can take node 7, which is again minus 38. Let's consider node 6, and then we take the node 6. What happens? If I take x1 is equal to 1, that means my weight becomes 21, which is more than 15, so I can't even consider it. Same way, if I take x4 is equal to 0, so if I take x1 is equal to 1, weight becomes 21, which I can't include. Or if I take x4 is equal to 0, that means I cannot get any more elements. So my value, my cost would become 10 plus 10 plus 10, 12, 32. And since this cost is greater than my upper value, so this cost minus 32 is greater than minus 38. So I will not consider this node, and I'll kill this node as well. So that means node 6 we're not going to explore because not giving us anything. So let's explore node 7. Node 7 will have two children, either include x4 is equal to 1, which is node 8, or when x4 is 0, when x4 is 0, that becomes node 9. And so my live nodes are right now only 8 and 9 and nothing else. So what are my live nodes now? 8 and 9. So let's compute those values for 8, 8 and 9. Node 8, by cost to taken would be, look, for node 8, this x3 is equal to 0. That means we are not considering this. So my cost would be, if you look at 10, 10, 18, since my weight is 2 plus 4 plus 9 is 15, so I include the cost, all the weight equal to knapsack, so I take all the weights and my cost becomes minus 38. Similarly, my upper bound also becomes minus 38, which remains the same, and I'm fine. So for the node 8, my value becomes 38 and 38 as before. As you've seen before, every time we consider a left child with variable is equal to 1, the value of cost and upper bound will remain same as the previous parent node. Let's look at node 9. If you look at node 9, what we're saying is, for node 9, we are neither considering weight 3, neither we're considering weight 4. Thus, my cost would be 10 plus 10 minus 20. My upper bound also would be 10 plus 10 minus 20. Now look, this cost minus 20 is greater than my upper bound. So that means I need to kill this node and don't consider it. And upper does not change, we can kill that node primarily. Now load 8 and 9, it is the leaf nodes. Least squad is node 8 and 9 doesn't have to be considered. We can kill it right away there and that could be fine. And that basically means my answer node is, because that is the leaf node, my answer node is 8, where my upper bound is 38, my cost is minus 38, that gives the answer. And since, if you look at my path, what is my knapsack path? x4 is 1, then x3 is 0, x2 is 1, and x1 is 1. So my tuple value would be 1, 1, 0, and 1, and that gives me the answer for this. Now we had explained to how to compute Cx and Ux, but mathematically if you look at the programs, we can probably write two functions called bound. Bound would be used for cost and upper bound would be used for the upper bound, and we take values as negative, so they are defined in the next slides as below. Essentially we are saying, if you look at, we give the current value, so far we compute it, and for remaining nodes compute. Essentially we are saying, take all the weights remaining, keep adding them to that, and if it becomes less than, keep adding it, and if it is more, then basically use the partial weight. They were doing partial weight. So this gives me the cost. This is used for cost, and for my next function upper bound, this is used for my upper value, or called Ux, which we are computing that value. Only difference in this case from previous cases, we basically will not take the partial weight of when it exceeds. So when it exceeds Wi exceeds this, we will not take that value and basically return at that point. So in summary, what we have done, We have explored 0-1 knapsack problem using least cost branch and bound. That means we are building a tree, state space tree, and we add the live nodes into a heap, take minimum node out. We don't explore the node the way they're ordered, but we always took the least node. And anytime the cost value of a node becomes more than my best known solution, which is my upper value, then I kill that node and then proceed. And this way, in the next lecture, we'll look at the FIFO implementation, which is first in, first out. We'll look at that scenario and then we explore.